Our last topic in this unit is the discussion of basic organization and understanding of the periodic table. The periodic table is a very powerful organizational tool that also contains a lot of information about relationships between the elements, which you'll recall earlier are the basic building blocks of all matter. Now, the history of the periodic table is a somewhat interesting one. By the mid to late 1800s, there were approximately 50 to 60 elements that had been identified very clearly as being the simplest possible forms of matter. If you look at your periodic table, you notice that there are over 113 elements currently listed on the table, which means we almost have twice as many now as we did about 150 years ago. Now, the reason for this is that subsequent to the very first periodic table, there were other compounds that were then identified as being elements, and then subsequently man developed the ability with the advent of technology to actually create artificial elements, elements that do not exist in nature. If you look at your periodic table, all the elements that exist after the element uranium are called the transuranic elements, and those are all artificially created. They don't exist naturally, they're only created in a laboratory. Okay, but going back to the very first periodic table, there were a number of scientists that had made some different attempts to try to organize all of the known elements in some way that would best way to display the relationships between them. The one that was the most successful was a man named Dmitri Mendeleev. He was a Russian scientist, and he published a book in the 1880s that talked about how the principles by which he developed the periodic table. What he has is he stated what we call the periodic law. Remember, a law is a description of a pattern or process in nature. The periodic law basically said that when the elements were placed in the order of their weight, in other words, from lightest to heaviness, repetition of properties could be seen. Okay, so Mendeleev basically said that when he started laying out the elements from lightest to heaviest, at a certain point, you'd see an element appear that had a lot of properties in common with an earlier and lighter element. Now, when we take a look at the periodic table, and you can probably get yours out and take a look at it as well, this is what the periodic table looks like. Now, this is not exactly the periodic table that Mendeleev developed, but it works on the same principles here. So, for example, let's look at this row right here. It starts with lithium, beryllium, it goes boron, carbon, nitrogen, oxygen, fluorine, neon. These elements, when you lay them out, okay, once you get past neon, you go back here to sodium. Sodium and lithium are very, very similar in both their physical and their chemical properties. So Mendeleev, when he was listing them out, said, look, sodium and lithium seem to have a lot in common with each other. So I'm going to put sodium underneath lithium, and then he just kept listing them out. Okay, and then I'm going to cross potassium. Potassium is very, very similar, although not identical, to lithium and sodium. So we put it here. So he figured after a while he was on to a particular pattern. Now, not all of the elements that you see here were in Mendeleev's original periodic table, because some of them were then identified later. And these elements down here and these elements here. Okay, and I know your periodic table shows some more elements over here. Those were all created long after Mendeleev published his table. Now also, Mendeleev's table had some holes in it. Okay, there were some elements that just didn't fit the pattern, and he had to shift them over a little bit. Okay, so for example, the element germanium had not been isolated and identified as an element when Mendeleev published his table. But he knew that gallium had a lot more in common with aluminum, and arsenic had things in common with phosphorus. So he decided to leave a hole here because there wasn't an element. Originally, gallium and arsenic were right next to each other. So he shifted it over and left a hole. There are a couple of holes in Mendeleev's table. But the important thing for you to remember is that you see this repetition of properties, and that was what Mendeleev used and what he called the periodic law. Okay. So let's go back to the table real quick. The rows are what Mendeleev called a period. That's what he meant by the periodic repetition. Okay? Periodic means something that happens at regular intervals. Okay? And the columns are called groups or families. So column is called a group or a family. Now, the reason they called them families is because if you think of your family, you have a lot of things in common with the other family members. You're not identical to your other family members unless you happen to be a twin. But you have a lot of things in common with your family members. And this is very key because when we look at elements in a family, elements in a family, have similar, but not identical, chemical properties. Now, why didn't I say chemical and physical properties? Well, when we look at some of these groups or families on the periodic table, some of them do have a lot of physical properties in common. However, some of the families have very little in common as far as their physical properties. However, every family has similar chemical properties. Now, one of the things that Mendeleev looked at, which means that the formulas of the compounds they make are like. Okay, you're going to watch another video, not one of mine. This is one made more professionally, and you're going to see a little bit more about, explain a little bit more about what do I mean by formulas of compounds that they make are alike. But this is what Mendeleev used to bolster up this idea, because a lot of his fellow scientists could see that some of these families all looked alike. They had chemical and physical properties in common. So it made sense to them what Mendeleev said, I want to put these together in a family. Some of the families didn't have hardly any physical properties in common. So Mendeleev at first was like a little unsure whether he should put them in a family. But when he looked at how they behaved chemically, what they reacted with, what they didn't react with, and the proportion or ratio of atoms of these other elements that they reacted with to make these compounds were very much alike, and he felt very confident that the pattern he had identified was the best possible pattern. Now, we're going to go back to and look at, there are these groups or families on the periodic table that have names. Let's go back to our periodic table. And I highly suggest what you do right now, if you haven't done so already, is you get out your periodic table and you make some little notes somewhere about what are the names of the different families, the names of the different columns. Now, I'm going to erase this off here. I wrote earlier. give myself a little bit more writing room. Okay, now remember we said that the families are they are the columns. Now this first column here are called the alkali metals. Okay, we will come talking a little bit about what are metals. They're called alkali metals, okay, because they all form compounds that are what we call basic. You may have heard of acids. Okay, acids and bases are compounds that have some properties in common with each other, and they tend to neutralize or cancel each other out. Because you know that like acids burn and eat through metals and things. Well, you put acids and bases together, they kind of cancel each other out, and they make new compounds through chemical reaction that don't have any acid or base properties at all. So if you put an acid and a base together, you get something that's perfectly harmless as far as you could pour it on your skin that wouldn't cause you any damage. So these metals tend to be found a lot in compounds that are called bases. Another word for base is alkali. So these are called the alkali metals. Now that's lithium, sodium, potassium, rubidium, cesium, and francium. The next column right next to them are almost like cousins, these two families, because they are so much alike in so many ways. And this family, its name is only a little bit different. These are called the alkali earth metals. So you can guess they probably also form compounds that are called bases very commonly. They're called earth metals because these are also commonly found in minerals. For example, beryllium. Beryllium is one of the main components in our colored precious stones. We find beryllium in sapphires and rubies and amethysts. You find beryllium in there. Okay, magnesium and calcium are very commonly found in minerals, and these two here, particularly magnesium and calcium, are often found because they'll dissolve in water fairly well, and they make our water hard. So if you have hard water and you need to have a water softener, it's because your water contains a lot of dissolved magnesium and calcium compounds. These are commonly found in the ground. Now, the next family is this big giant group in the center of the table. This is one big enormous family. These are called the transition metals. These are most of the common metals, so when you ask somebody to name a metal, okay, they might name this little column here, copper, silver, and gold, very common. Zinc, mercury, here's iron. Okay, these are common metals that we're very, very familiar with. Okay? Some of them you've probably never heard of before, like maybe hafnium, okay, or molybdenum. Zirconium, you may have heard of cubic zirconia, which is like fake diamonds. Okay? That's because they have zirconium in them. That's where the name comes from. Now, these were originally like subfamilies along with Mendeleev's original families. And then they all got put together in one giant family because Mendeleev's table kind of got a little weird, and some people figured they could tweak it and make a better and neater looking arrangement. They're called the transition metals because as we move from left to right across the table, things are all metals, and eventually things are going to change to more non-metal-like in the properties. So these kind of transition between the very strongly metallic elements into the less metallic elements and eventually the non-metals. So these are called the transition metals. Now these next columns over here, the next four columns, are simply named after the very, very first element at the top of the column. So this is the boron family. This family is the carbon family. This is the nitrogen family. And this is the oxygen family. Okay, so these four columns, the first four columns after the transition metals, are just named after the element at the very, very top of the column. Now, the oxygen family is occasionally have an odd. You will find it, though it's not very commonly. Sometimes you see the term chalcogens. But I'm not going to make you responsible. I will not put that on a quiz. I would rather you call it the oxygen family. Okay, now these families are the ones that don't have a lot in common physically, but they behave the same way chemically. They have similar chemical properties. Okay, this column right here, these are called the halogens. The The word halogen means salt former. So these compounds, when we start talking about things, the word salt to a non-chemist means one compound, sodium chloride. There's chlorine right here. However, to a chemist, salts are a big, giant group of compounds. And a lot of the salts have these members of the halogen family as part of their compound. That's where the name comes from. Okay, this is an unusual family in that it has fluorine and chlorine are gases, bromine is a liquid, and iodine is a solid. Okay, astatine is highly radioactive and unstable. So there's only tiny, tiny amounts of astatine that exist in nature. Okay, this last family over here on the right, these are called the noble gases. As you can tell by the name, they're all gases at room temperature. The term noble comes from the fact that these are called the non-reactive gases. Just like the nobility in many aristocratic societies wouldn't go and mingle or marry with anybody except themselves. They just didn't, they didn't interact or react with anybody else except other noble gases. Other aristocracy. Now, the noble gases don't react with each other. In fact, they just pretty much don't react with hardly anything at all. We can get krypton and xenon to form a very few compounds with very, very, very highly reactive other elements, but no compounds at all have ever been made with helium, neon, and argon. They just always exist as elements. They won't bond. Okay, there is one more family on the bottom, and that's these two rows down here. Now, if you look at the numbers, we'll talk about the numbers very quickly, you'll see that this section right here actually fits in between these. Okay, and they just moved them down here just so the periodic table isn't quite so wide. This entire group down here, these are called the inner transition metals. You also see the term occasionally rare earth metals. Now, everything, remember, past uranium is artificially created. So only this first row and the first three elements here actually occur in nature. They are very, very rare, okay? And they are also found in minerals. They have to be mined out of the ground. That's where we find them. Okay, so that's where the term rare earth metals come from. This particular first row here is sometimes called the lanthanides, because if we inserted them into the table where they belong, the lanthanum would be the first element in the row, and the second row down here are sometimes called the actinides, because if we put them back in here, this row, this will go right here, right after actinium. So the lanthanides and the actinides. You don't really have to know that, but it's just kind of interesting. Okay, now a little bit about, now those are the 10 families on the periodic table. Now we're going to look at a little bit about what do you see in these boxes. Now if you look at the box in your periodic table, you get some information. At the very, very top, you get the name of the element. Now you'll have to become familiar with all the names. You do not have to memorize the periodic table. In fact, you'll be allowed to use your periodic table on your quizzes and your exams and everything. We're going to write lots and lots of stuff on it all semester long, so don't lose it. But you don't have to memorize it. Okay, but you better become familiar with it, which means you have to spend a lot of time looking at it. Okay, the first thing you see is the name, and in the middle, you'll see one or two letters. These are the symbols for the elements. If there are two letters, the first one is always capitalized, the second one is always lowercase. If there's only one letter, then it's always uppercase. Now, usually the name and the symbol kind of go together, but not always. Sometimes it's because the symbol for the element comes from a very ancient name for the element. For example, if you look up the element iron, you'll see the symbol is the letters Fe. Now iron begins with I. The symbol is not I, because the element with the symbol I is a different element called iodine. The reason iron symbol is Fe is because iron is a very ancient element. Okay? It's one of the very earliest recorded elements we have working with, and the Latins called it ferrum. That was the Latin name for iron. That's where the symbol Fe comes from. Some of the other symbols and names that don't quite go together are because the element symbol comes from a mineral from which the element was purified. For example, if you find the element tungsten, which is in the middle, kind of the bottom left a little bit of the transition metals, it's an element called tungsten. The symbol for tungsten is W. The name and the symbol don't match at all. It's because the element tungsten was purified from a mineral that was called wolframite. So that's where the symbol comes from. Now, there's other pieces of information in the box. Okay, first of all, there is a number here above the symbol. Okay, this is called the atomic number. Okay, and if you look at your periodic table, you notice it starts with the number 1 in the upper left-hand corner, hydrogen. And as you go from left to right, okay, across the rows, and then you move it down, you'll notice that they just count up. These are whole numbers. We'll come back a little bit later and talk about exactly what does the atomic number represent when we get to our next unit on atomic structure. Okay, and then there's another number underneath, and this number has a decimal point usually. Okay, this is the average atomic mass. This gives you some idea of the weight of the element. Okay, we will come back to a little bit more about how do we calculate this in atomic structure. But if you look, see, originally the atomic numbers were not known when Mendeleev put together his table, but the average atomic masses were pretty well defined. Okay, we, of course, we have more significant figures now because we have better instruments, and so we're more accurate. So Mendeleev put everything together using the average atomic mass. He didn't know about atomic number yet. Okay, and then when the atomic number was determined, exactly what it was and what it represented, then they match it pretty closely. However, there were a few elements in Mendeleev's table that had to be switched because their atomic numbers were out of order, even though their atomic masses were in order. Okay, so again, I will remind you today that all of the elements that are in a column have common chemical properties. Now, where do they get the chemical properties? Chemical properties, or how elements react with other elements, come from something called valence electrons. Now, we will talk about subatomic particles when we talk about atomic structure. Okay, but valence electrons are a specific subset. They're just some of the electrons that an atom has. We'll talk about exactly what they are and where do you find them and how many do the families have a little bit later. But you need to remember right now is that families, these are columns, similar chemical properties, remember similar but not identical. And that comes from the same number of valence electrons. Okay, now let's look at a couple things that are interesting for you to note in the periodic table. Okay, first of all, some elements we said on the periodic table are not very reactive. Okay, we talked about our little friends, the noble gases over here. They are very non-reactive. Okay, however, there are some elements that are the very opposite. They're extremely reactive. Okay, and our very, very reactive elements are here and here. Okay, so these are relatively non-reactive. Okay, and so are these. These are non-reactive. Okay, so the non-reactive elements are here, the noble gases, kind of here in the center. Okay, over here, these are the highly reactive metals, and these are highly reactive nonmetals. Now, one important thing for you to note here, okay, is this element up here. This is the element hydrogen. Hydrogen is not a part of any family. Okay? It's not in a family. It's all by itself. Now, true, it's sitting on top of a family. It's sitting on top of the alkali metals, but it's not an alkali metal. So why does it sit here, and why is it not in a family? Well, it sits here because it has the same number of valence electrons as the alkali metals. But oddly enough, it has nothing else in common with them. It doesn't behave chemically the same way. It's kind of similar, but it does some different things chemically that the alkali metals don't do. Okay, and it also has absolutely no physical properties in common with this family. Okay, so it's kind of the stepchild of the, kind of the orphan of the periodic table. It doesn't have a family that it belongs to. Now, we said earlier that we have these things that are called, we said that that we can group. I started talking about these metal things. And so there's a question, and our first question is, well, what exactly is a metal? What makes elements on the periodic table metals? Okay, and if you're not a metal, then what are you? Okay, one of the things I want you to do right now is get yourself a nice thick marker or really heavy and dark. We're going to draw a line in a stair pattern along this part of the periodic table. Make sure you get yourself a marker and do this before you take your quiz. I'm going to want to see that you marked up your periodic table that you can use on your quiz. This is the dividing line. This is called the stair-step line. It divides the metals on the periodic table from the non-metals. Okay, elements on this side are metals. Okay, in fact, the more you go this way, the more metallic they become. This way, these are the non-metals. Okay, to the right of the line. Okay, to the left of the line are metals. Okay, so these are metals, these are all metals, these are metals. Okay, hydrogen. Hydrogen kind of messes things up. Hydrogen's on the left of the line, but it's a non-metal. So you gotta remember that. Everything to the left of the stair-step line is a metal, except for hydrogen. Now, there are also some of the elements in the periodic table, the ones that sit right along the dividing line between the metals and the non-metals. They're called the metalloids. We'll talk about what they are in a minute. Okay. This is a metalloid. This is a metalloid. Both of these are metalloids. Metalloids and metalloid. Okay. Now, what do I actually mean by the terms metal, nonmetals, and metalloids? Okay, metals, these are hard, they are shiny, they are solid, okay, they are bendable, and they're good conductors, okay, which means they conduct both heat and electricity. Now, these are very general statements. Some metals are softer than other metals. For example, the metal mercury is so soft it's a liquid at room temperature. Okay. Metals are being shiny. Okay. Some metals are much shinier than others. The technical word for shininess in chemistry is luster, L-U-S-T-E-R. That's shininess. Okay. Again, solids. Okay. That's kind of, most of them are solids, however, then some of them have low melting points and become liquid in the palm of your hand. Okay, bendable. Some elements are more bendable than others, but they're all pretty good conductors of heat and electricity. Copper and silver being the best conductors that we have. Silver is actually even better conductor than copper, but it's too expensive to use for wiring, so we use copper instead. So anything that has these properties is considered a metal. So most of the elements on the periodic table are metals, about 2/3 of them. All right, then what about the nonmetals? Okay, nonmetals, if they are solid, they're brittle, which means that they don't bend, they break. Okay, they're not shiny. They're often liquids or gases. and they're very poor conductors. Now, the elements that are in the middle are called the metalloids. They're like a border town. Okay? If you've ever visited border towns along the border between Mexico and the United States, the border towns tend to have elements of both cultures. Okay? You see foods from both the U.S. and Mexico for sale in the stores. People tend to speak both English and Spanish. And so the metalloids are kind of like border towns. Periodic table. Okay? They have properties that are either in between metals and nonmetals, or properties of both. So for example, the metalloid silicon. Silicon is brittle and shiny. So it's brittle like a nonmetal, shiny like a metal. It's also kind of a medium conductor. It's halfway between a good conductor and a poor conductor. A lot of the metalloids are used in production of computer chips. They are what we call semiconductors. The word semi meaning half. Okay, so that means that there is a lot more resistance to electrical current passing through them, which means we can control the flow of electricity. If we tried to make our computer chips out of just regular metals, they would just get too hot and the computer chips might melt or overheat. And metalloids are kind of in between. We can't make them out of nonmetals because nonmetals don't conduct electricity at all. So metalloids have these very, very unique properties, which actually makes them very, very valuable. Gallium and silicon and arsenic are very, very, very commonly used in making computer chips. So it's very valuable. Okay, so you will need to know, okay, that where are the metals, where are the nonmetals, and where are the metalloids. The metalloids are the tricky ones. So make sure, okay, that you know, okay, which of these little border elements are metalloids. Okay, aluminum is most definitely metallic in nature, so don't ever include aluminum in the metalloids. Everything else kind of borders right along here. Okay, acetine is much more non-metallic. We don't know a whole lot about it because, like I said, it's very rare. It's also radioactive, which means that it doesn't tend to stay acetine very long. The atoms tend to kind of fall apart and become other smaller elements. All right, so that's everything that you're going to need to know about the periodic table. Have fun studying.